Hello everyone, my apologies for getting this out a little bit late, but I wanted to go through our continuity note with you. Last time we talked about limits of a function existing or not, and now we're going to talk about the case where if a limit exists for a function at all points and the function is equal to that limit at a certain point, we say that this is continuous. And we have very specific criteria to say that if we have some sort of a function, real valued function, and a is some value, we say that f is continuous at x is equal to a if we have the three following conditions. The first condition is that f of a is defined. Okay, so we don't have an open hole, in other words. The other thing is that the limit as x approaches a of f of x exists, and remember, that's the case if the left and right-sided limit are equal to each other. And then the third thing is that not only does the limit exist, but it is equal to f of a itself. And if a function is not continuous at x is equal to a, we say that it's discontinuous at that point. Now, are there different types of discontinuities? And yes, there are. There's three main types. The first one is known as jump discontinuities. And this is where we have a function where, we're going along in one direction and all of a sudden, literally, there's a jump. There's a separation between the left side and the right side. So the left and right-sided limits will not be equal to each other. The next type of discontinuity is called a removable discontinuity. And this is where we have a situation where there's literally a hole in our function. Sometimes it's almost like that value is cut out of the function and pasted somewhere else, but these are two types of removable discontinuities, either a hole on its own or a hole and the function is defined at x but at another y position. The other one is infinite discontinuities, and this is where at least one of the one-sided limits shoot off to infinity. So the function could be following a vertical asymptote, for example, but maybe it's not going in the same direction, similar to like our 1 over x example that we've done a few times now. Now, how can we go about figuring out if a function is continuous or not? We have to go through that definition. We have to check the 3 steps. So let's go through and do that now for a few examples. So for this first one, and for the next couple, we're going to be given a graph. So we're not going to be given an equation, but we're going to be given a graph of what the function looks like. And I want to see if it's continuous or not at x is equal to 1. So let's go through the steps. Is f of x, does it exist at x is equal to 1? And we see by this little hole here that that is not the case. We have an open hole at x is equal to 1, which means our function does not exist at that point. So we would say that our function is discontinuous. Let's look at our next one. So this is a function called g of x, and let's follow the steps. Well, first, let's look at x is equal to 0 and see if our function exists or not. And sure enough, it does. So we see that g of x exists at 0. In particular, what value does it give us? It gives us -1. So now let's look at the second step. Does the limit as x approaches 0, does that exist? And because we have a piecewise function, we're going to have to look at the left and right-sided limits. So if I'm looking at the limit coming from the right side, so the plus side, I'm getting that this is equal to -1. But if I go from my other side, my left side, my negative side, I'm getting that the limit is equal to 1. So in this situation, since the left and right-sided limit of our g of x are not equal to each other, we say that the limit as x goes to 0 of g of x does not exist. So what does that mean about our function? It means our g of x is discontinuous at x is equal to 0. All right. Now let's look at this one. So we can already see if we look at x is equal to 4, this is probably not going to work out because I'm seeing something that looks like a removable discontinuity. But let's again go through the steps to see exactly where it breaks down. So first thing, does our h of x exist at our point? Yes, it does. So we see h of 4 exists. And in particular, what is it equal to? Our h of 4 isn't equal to this part. It's undefined here, but it's equal to 1, where that filled in circle is. Now, let's see if the limit exists. So we have to check the left side and the right side. And if we jump back quickly to our picture, we can see that regardless if I come down from the left or from the right, in both situations, I'm going to get that the limit is equal to -2. So -2, -2. Therefore, since the left and right sided limit are equal, our limit is equal to -2. But there's a breakdown now when I check if the limit is actually equal to the value of the function at x is equal to 4. So is this part true? No. The limit as x approaches 4 is equal to -2, but h of 4 is equal to 1. So we say this is discontinuous. All right, last but not least. When I'm looking at this function p of x, I can see right away that this is not going to exist because it shoots off to infinity. So our function is not even defined at that point. So p of x is discontinuous. At x is equal to 2. All right. So if we want to talk about a function being continuous on a closed interval, including the endpoints, we would have to make sure that it's continuous on the open interval as well as the endpoints. So I just want to look quickly at some of the functions that we've talked about over the last couple of weeks and see where they're continuous. And then we're going to do an example where we have a function that's continuous in most regions, except maybe at a couple points. All right, so continuous functions. So we mentioned when we discuss properties of limits that polynomial functions, these are going to be continuous for all x because they don't include holes or asymptotes. So for all x, these functions are continuous. For rational functions, the only time that we would have discontinuities is when we would have vertical asymptotes. So when our q of x is equal to 0. Otherwise, it's going to be continuous everywhere else. Radicals or root functions. In this situation, so long as we're in a domain that make the square root function or radicals positive, we are fine. We have a nice smooth function here, so it will be continuous in the region where our domain is actually defined. For exponential functions, these are functions that are continuous. There's no holes, there's no asymptotes, they just grow very quickly. And with logs, where logs are defined, so x is greater than 0, again, there's no problems. But logs are not defined in the negative region, so they can't be continuous in that region. And then here are our popular trig functions. So our sine and cosine, this is continuous, okay? We don't see holes, we don't see asymptotes. But in the case for tan, the parts where tan is not defined, okay, and these factors of pi over 2 here, they're not continuous, but everywhere else there are. They are continuous tan functions. All right. Now, let's look at a final example where we consider a piecewise function and we want to see where it's continuous and discontinuous. So this is how I've defined my piecewise function. Now, if you were already given the graph, we could tell very quickly where there's discontinuities. We could look at this graph here and see that there's going to be a discontinuity at x is equal to 3. Okay, there's a jump discontinuity. The left-sided and the right-sided limit are not equal to each other. But everywhere else along this pink line here, everything's nice and continuous. Along the green line here is continuous. And even at this interface here, x is equal to 1, despite that our blue line, that endpoint is not included, for this parabola here, 1 is included. So our left and right-sided limit are still the same, but our function is also defined and equal to that limit there. So it's still okay. So because the actual separate parts of the piecewise function are all polynomials, they'll be continuous. We only have to check the endpoints. So the parts that we're going to have to check are x is equal to 1 and x is equal to 3. And at x is equal to 1, we see that our function is defined. It's equal to 2. The left and right-sided limits are the same. And the limit, as x approaches 1 of f of x, is equal to f of 1, is equal to 2. So our function is continuous at 1. The only place along all of x that this is not continuous is at 3, because we have a jump discontinuity. Our left and right-sided limit are not the same. Okay, and here's just a little bit of explanation on how I plotted these things. I know roughly what a line looks like and a parabola looks like, but I needed to see what these functions were at specific points so I could easily draw them. And here are the points there. All right, I hope you found that helpful. Thank you very much.